Hi, welcome to Math317 Operations Research, lecture 11, I think. New homework should go in the pile above the campus mail envelope. Old homework is next to it. Solution keys is next to that. While people are settling in, I will talk about something I have recently tried to optimize in my life. I am one of the coaches of my son's baseball team, and the league has a hard rule that you cannot start a new batter if you've thrown 75 pitches so far that weekend. And so given that some teams only have one dominant pitcher and then almost no one afterwards, I have been able to convince the coaches to give all of our kids who are, say, 7th and 8th graders on a team up to 10th graders, do not swing until the umpire calls the first strike. And just you eat up the pitch count. And we faced two strong pitches this weekend. Implementing it the second day, we knocked out the ace inning earlier. I think we could have come back on the first day, and I know this is being recorded, if when the pitcher was at 73 and our batter went up to start the final inning and was told, do not swing at the first pitch, because the only thing we can't have you do is a one-pitch pop-up, because then you can face two of our batters. Swung on the first pitch, popped up to the catcher, which allowed their ace to then face our next batter. 2 outs, down 2 runs. We then get several walks. We're threatening, but do not quite make it on a called third strike. And so this would have been a great opportunity for analytics. But the problem is you still need the people to, what? Listen to you.
How old are these kids?
They are 12 to maybe 16, 17. They are old enough to start knowing stuff like this. And if you're in a league with a pitch count, it is extremely important. So one of my jobs is to tell, we have to pull our pitcher right now, because if we don't pull him now, you can't use him the next day. It is amazing the differences something like this can make. I think we had a real chance of winning that game if we had knocked out their ace one batter earlier. Question? Or?
Are the players fully informed as to the rationale behind it?
Yes, they're absolutely informed. And we actually even talk in the dugout, and I will risk having this said on, that if you get a favorable count as a batter, let's say it's 3 balls, 1 strike, what kind of pitch is he going to give you? We've got some people who bust
A ball.
Oh, what kind of ball is he going to throw if you have a 3-1 count? 3 balls, 1 strike. What does the pitcher have to do? I need some baseball knowledge here. Right in the middle, you got to make sure it's a strike. It's going to be a nice marshmallow. And so one of our hitters who has not had much success, he's 7th grader, he got the marshmallow on 3-1 and had a nice hit into the outfield. I think, oh my God, yes, it changes what pitches people throw. And these are the small little things you want to be looking for in life. What things can you do without too much trouble? With little kids, you cannot convince them of a whole slew of things. The number of signals that they have missed with, okay, now, what did that mean again? It's a nightmare. Don't try to do something like that, but something very simple. Don't swing until the umpire calls a strike. They should and can remember something like that. We might talk about card counting and blackjack maybe later in the semester. There's a lot of great algorithms to do this. The best algorithms are not practical to use for most human beings. The simplest ones do not do as good of a job, but they're very easy to implement. A king, queen, jack 10 is a +1, a 2, 3, 4, 5 is a -1. And you keep a running tally to get a quick sense of, is the deck more stacked towards low cards or high cards? Now, ideally, you want to keep track of everything, but that's a lot more work. So just as we continually search for efficiencies, you want to think about what can you actually implement without too much trouble. All right. So speaking of efficiencies, we're going to see if moving the rotating desk will help keep things focused. So we want to do today more stuff on phase 1 and phase 2. So we're trying to solve canonical linear programming problems. Canonical linear programming problem. And it's going to only be slightly different than what we've seen before. And I think there's a typo in the book where it says row at one point, which should say column. So we have AX equals B, X greater than or equal to 0, and we want to minimize C transpose X. We're going to assume B is not a linear combination of less than m columns of A. A is m by n. We're basically just avoiding degeneracies. So if you have a very large matrix m by n, it's possible maybe B is one of the columns. Or maybe it's a linear combination of 2 of the columns. We want to stay away from something like that. We don't want B to lie in a lower dimensional subspace. 3, we're going to assume B is greater than or equal to 0. We always have to be careful about what happens every time we add an additional assumption like this, an additional normalization. Can we do this? Well, we have AX equals B. If one of the entries of B was negative, just multiply the corresponding row of A by -1. So it's not a big deal. So we can handle this without any trouble, and it just gives us a way to adjust things a little bit. We will assume that M is less than N, so we have underdetermined system. Okay, and then was there one more that we wanted? No, okay. Yes?
Are we not going to assume no non-zero columns?
So we'll assume no non-zero columns. And then there's one last one. The rows are linearly independent. If we had the rows were linearly dependent, we could have an inconsistency. Imagine you had the same row twice, but with different values of B. You know, I want 3x plus 4y to be 7, and I want 3x plus 4y to be 9. It's very easy to find all feasible solutions. There aren't any. Or you could have 3x plus 4 equals 7, 3x plus 4 equals 7. Well, then you don't need the row the second time. So you always want to look at, is there anything severe by any of these assumptions? No. You know, this is basically just making sure we stay away from degeneracies. We don't want to be in a situation where it's not worth the effort. If the system AX equals B is inconsistent, there will be no solutions. So there's really no point in trying to find optimal solutions when there aren't any. So we're going to just stay away from those situations. Okay, any questions about this so far? Right, this seems to be moving somewhat well today. All right, can somebody tell me what phase 1 is again? Yes?
Finding a feasible solution or finding that none exists.
Finding a feasible or none exist. Be a little bit more specific about how none exist. How do we find that none exist?
Finding a sequence of
Good.
feasible solutions where the cost is negative infinity.
By finding sequence with cost going to minus infinity. So not only does a feasible solution not exist, you give me any value, and I can give you a finding a feasible solution.
I think that's how you showed phase 2s.
Right, I was going to say, phase 1 is finding, okay, so wait a minute. Now I'm confused. We have phase 1 and phase 2. The problem is they're so circular. You know, we are trying to find an optimal solution. So phase 2 takes as input a feasible solution and then finds an optimal solution or shows that none exists by having a cost going to minus infinity. So I think there was no need to go over here. It's finding a feasible solution or show that none exists. And it will be done by finding a sequence with cost going to minus infinity of a related problem, I believe. All right, and then what's phase 2? So what do we get to assume for phase 2? Yes?
Assume there is a feasible, find an optimal, or prove that none exists by then.
Right, so given feasible, find optimal, or show none exist by finding a sequence with cost going to minus infinity. Okay, so we're going to show given 1 we can do 2, and given 2 we can do 1. And this does look circular. It's not circular because we don't use the same problem each time. So if you can happen to find a feasible solution, then you can run the phase 2. The challenge is it easy or is it hard to find a feasible solution? We talked last time at length about some situations where it is trivial to find a feasible solution. Just to recap, somebody give me a situation where it is trivial to find a feasible solution. Yes?
B is 0.
Well, no, I mean, I've got to give you, you got to give me a problem. So you want to say B is 0? Okay, so if B is 0, then take x equals 0. So that would be definitely a feasible solution. Give me a real world problem where it's trivial to find a feasible solution.
Like how to optimize like the revenue you make by selling tickets.
Yeah, how to optimize the revenue by selling tickets. What's a feasible solution? I'm sorry? Sell no tickets, right? You're not going to stay in business long, unless you're a front for another organization, but that's a different type of problem. So there are certain situations where we can trivially find a feasible solution. If you could choose your matrix A, what would be the nicest matrix A that you could choose? Yes?
Identity matrix?
Yeah, identity matrix. Now in general we can't do that because M and N are not going to be the same. But imagine A was the identity matrix. It would be pretty easy to solve x equals B. Right? In fact, as soon as I write down the question, the solution is there. That's what we're going to do. We're going to augment our matrix A and come up with a new related canonical linear programming problem which we can solve trivially. And then we're going to go from the feasible solution to that related problem to hopefully a feasible solution to the original. So assume can do phase 2. So now we look at AX equals B, X and B are greater than or equal to 0, and we want to minimize C transpose X. Now, we can run phase 2 as long as we have a feasible solution. Right now, I don't know what feasible solution is because this is just a general problem. So consider the new problem, AI xz equals B. X and Z and B will be greater than or equal to 0, and we want to minimize 1 transpose Z, which is Z1 plus Zn. I'm sorry, Zm, I believe. Okay, so this is the key idea. We choose a related linear programming problem where the answer is staring us in the face as to what the feasible solution is. So what would be the feasible solution? So you have to give me the vector xz that works. So what should x be? What should z be? So when we multiply this out, we're going to get ax plus iz equals b. What should we choose for x? What should we choose for z?
X should be 0, Z should be B.
Right, so take x equals 0, z equals b. This is essentially what I was saying a moment ago. If we have, x equals b, it's trivial. The only difference now is instead of using the letter x, I'm using the letter z. Is there a cost to doing this? Question.
Oh, I didn't say the inequality, or I thought it was a strict inequality, not mixed equal.
Okay. So all I'm doing is I'm using the letter z rather than x now. So I've added a lot of variables. But by adding these variables, it's trivial to see a solution that works. Take x to be 0 and take z to be b. And now This should answer a question about that list we had where the third item was we want b to be greater than or equal to 0. We never said that before when we were talking about a canonical linear programming problem. Why do we want b to be greater than 0? So what's the purpose of having b greater than 0? Greater than or equal to 0?
We want our solution to be greater than the 0 vector.
Yeah, we want the vector x and z to have no negative components. So it's essential that x and z have no negative components. If b had a negative component, if we tried to solve z equals b, we're in trouble. So there is a feasible solution. We can stare at this and it's going to scream at us, take z to be b, take x to be 0. Now, we want to minimize the cost, which is z1 plus zn. What is the smallest possible value for the cost? I don't know if I can attain it, but what is the smallest possible value could be? 0. Okay, so we know cost is at least 0. In particular, we don't have to worry about a series of solutions going to minus infinity. That can't happen here because the cost can't get below 0. Okay, that's nice to know. What would happen if the cost is 0? What's the only way the cost could be 0?
B 0.
If, I'm sorry?
Or B is 0, or both, and then Z is 0.
If z is 0. So if z is 0, then that means we have to be able to find an x such that ax equals b. And then we found a feasible solution to the original. So if cost is 0, then z equals 0, and the corresponding x is feasible for the original problem. Right? That's terrific. So all we have to do now is show that for a given problem, if we want there to be a feasible solution, there's got to be a solution where z equals 0. Okay, so unfortunately something has to be erased, either the phase 1 or the phase 2. I'm sorry, either the phase 1, phase 2 sheet or the statement of the canonical linear programming problem. I will assume by now people are familiar enough with the canonical linear programming problem that this is a lower priority and can be erased. So we are assuming we can do phase 2 whenever we can do phase 1. And since we have a feasible solution, we can now run phase 2. So run phase 2. Cannot have cost going to minus infinity. That's wonderful. So there must be an optimal solution. Therefore, there exists an optimal solution. We'll call it x opt, z opt, because we have no originality. All right? There are two possibilities. Case 1, z opt equals 0, so cost equals 0. Well, in that case, that implies x opt is feasible. Because every optimal solution has to be feasible, so we know AI, x opt, z opt equals b. If z opt is 0, then you get a times x opt is b. And this just implies a x opt equals b. So in the case when the cost is 0, or equivalently when z opt is 0, we found a feasible solution. So the only case that remains, case 2, z opt is not 0, so the cost is greater than 0. What do you think holds in this case? So now we know the cost is positive. Could there be a feasible solution to the original problem? If there was a feasible solution to the original problem, you're shaking your head, why can't there be a feasible solution to the original?
Because then this wouldn't be optimal.
Right, this wouldn't be optimal. If there's a feasible solution to the original problem, you can pad it by putting in a bunch of zeros for the z's. And what would the cost be? It would be 0. Cannot be a feasible for original as that has, z equals 0 and cost equals 0. And we're done. So, yes?
Could you please run through case 2 again?
Sure. So imagine that there is when we run through phase 2, we get a z optimal that's not 0. So if z optimal is not 0, it's got to have at least one positive component. So the cost has to be greater than 0. If there was a feasible solution to the original problem, just ax equals b, well, we can pad that by putting in a bunch of zeros here, and then we would have ai, x 0 equals b. It would be a feasible solution for the expanded problem that we're looking at, and because all of the z's are 0, its cost would be 0.
So is that sort of like a contradiction?
It's a contradiction. So over here, if z optimal is not 0, the cost is greater than 0, but if there was a feasible solution, the cost of the feasible solution is 0.
And we assumed feasible...
We're talking about feasible at different times for different problems. Right now we're talking about a feasible solution for the original problem. So we've got the word original over here. Because any feasible solution to the original problem can be trivially extended to a feasible solution for the new problem with a cost of 0. Because the x's have no interaction at all with the cost of the new problem. They do for the original, but we are forgetting about the original cost function. Nowhere in this proof do we use the vector c. We are only looking at the vector 1 dotted with z. The cost is entirely coming from the z's. And so if we are able to get a feasible solution to the original, we can get a feasible solution to the new with a cost of 0. And if when we run phase 2, we get that the optimal solution has a positive cost, then that contradicts the existence of a feasible solution to the original. Yes?
How come we chose, I guess, all the way back there for that to be the
Let me
cost?
just slide down. Okay. How do we choose this to be the cost?
Yeah, just like the 1 transpose to be...
Method of divine inspiration.
Okay.
So, this
It
is
doesn't work.
this is where the key idea is. It's coming up with this related problem. So we are padding it by putting in an I. Now the nice thing about choosing this as your cost is it doesn't involve the x's at all. And because it doesn't involve the x's at all, then if there's a feasible solution for x, in some sense, that's not going to interact with this at all, and that's going to be a cost of 0. And so it's going to give us a nice way to determine, could there be a feasible solution to the original? Now we have not used the dual problem yet. That's probably got to play a role somewhere in the proof, given that we mentioned it earlier. So that's something you should have in the back of your mind. At some point, the dual problem's got to make an appearance. But right now, the algebra here is not that bad. The difficulty is thinking to do something like this. And I'm hoping you're beginning to appreciate the power of a good canonical form. So we're not doing all this terrible case analysis. That we can assume now that b is greater than 0, so everything is aligning perfectly. So this is the proof of phase 1. All we have left to do is now prove that we can do phase 2 if we can do phase 1. So we can always find a feasible solution. I'm not going to go through that today. Now, after we prove phase 1 and phase 2, the next question is how long does it take them to run? If it takes too long for them to run, then it's not practical. I'll try to say this because this is a liberal arts school. There are certain departments that have different academic investigations than the sciences. And there might be some departments that talk a lot about relativism. For the most part in sciences, you really don't hear that word. There is a place for words like that, relative to your computing power. Is the problem easy or not? Did I tell you the story about the first time I was teaching statistics at Brown with the textbook? Okay, so I was at Ohio State. I was moving to Brown in a few months. I wanted to be a good doobie and start preparing some of my lectures. I kind of like to get more jobs in academia. And so I got a hold of an early version of the book. And at one point, we have this problem in probability, and we have to do some combinatorics, and we get a binomial coefficient. And the book says, you might think you've solved the problem at this point. I go, I have solved the problem at this point. And the book continues, but we're not done yet. Yes, we're done. And the book says, you now must evaluate the binomial coefficient. I'm going, what do you mean? Oh, when was this book written? And I flip back to how old the book is, and back then you don't have calculators. It was an old edition. And so to actually calculate the factorials was a non-trivial problem back then. Now, not an issue at all. The power of our cell phones, I think, is close to equivalent, if not better, than the Voyager space probes. So when you talk about what can and cannot be done, it's extremely important to remember that what can and cannot be done now could be very different in 5 or 10 years. This is the threat of quantum computers, that a lot of things that seem secure now could fall very easily in the near future. This is why, for a lot of things in cryptography, if you crack some code, you don't tell people that. Because not only will they stop then using the code that you've cracked, but they will now know that if you've intercepted previous messages, you can go back and decipher them. You don't want people to know that you can go back and decipher what they were doing. Sometimes these things are still valuable. Anybody know typically how long you have to wait for some military archives? Decades. I think it's like 40, 50 years for a lot of things. But it was a while before a lot of the World War II histories accurately reflected the role that mathematicians and cryptographers played. And that was kept secret, so people did not know precisely what could and could not be done. All right, so the point of this is I am not going to prove to you that the simplex method runs efficiently. That would take up too much of the course to do this, and I don't think you want to see that much technical detail and technical analysis. Unless you have that, you have one of two options. Trust it on faith, or try a variety of problems and see that it runs at a reasonable time. And then if you're applying it in the real world, well, just run with it, and if it returns a value in a reasonable amount of time, does it really matter if there's a theoretical proof certificate that says it's efficient? No. As long as it's always working in... Now, yes, you could then have a situation in the future where you really need the result and it's not coming, but if it keeps working and working and working, that's often good enough. All right? So I just want to be very clear about what we are and are not going to do. So what I want to do instead is I want to talk about another algorithm. I'm not going to prove how efficient it is, but if you want, I can show you exactly where to look to have an outline. If the construction had been done on time, I would have my office, and I would have all the books and stuff in storage, which would include the homework problems I did as a sophomore at Yale in real analysis. It was exercises, I think, 16, 17, 18, chapter 3 in Rudin, Principles of Mathematical Analysis, often known as either Baby Rudin or the Blue Book. Phenomenal, phenomenal book. This is the set of homework problems that moved me from physics to math. So it's Newton's method. How many of you are familiar with Newton's method? It's always better when the professor's hand doesn't go up. Okay, this is one of the best methods we have. Yes?
Did you just remember a homework assignment from 20 years ago?
Yes. That's how good the homework assignment was. I even went and I talked to the professor about it because 316 and 318 kicked ass. And 317, it was okay, but it wasn't great. So, yeah, Rudin probably just made up that problem, just have something else to compare, so you could just see how great Newton's method was. It is phenomenal how fast this works. And so if you're interested, you can actually read in an afternoon very easily how Newton's method works and why it works so quickly. And that's why I want to do this problem instead, to show you, here are some of the techniques we can do, and here are some of the issues. So, divide and conquer on one side, and Newton's method on the other. How many people have heard of divide and conquer? Right. This is often very famous, binary searches like this, where you often have a situation where you split in the middle and see am I above or below. So for instance, if I have an honest student in the class, I can guess your birthday in 10 questions, where if I'm wrong, you have to say earlier or later in the year. So I won't go all the way to get your birthday. Does anybody want to play? All right. Were you born on July 1st?
No,
No. Earlier or later?
earlier.
So what have I now done with one question? I've eliminated 50% of the days. That's not bad for one question. Were you born on, so I got January, February, March. Well, February is a short month, so I'll go with April 1st. Earlier or later?
Earlier.
Earlier. So with that question, I eliminated 50% of what's left. 2 to the 10th is? Yeah, we only have 366 days in the year. I'm not worried at all. So I'm going to stop here so we don't have your birthday publicly. So we have to keep asking you questions throughout the year that will slowly illuminate what your birthday is, but not be clear that that's what we're doing. Okay? What is the stupid way to get someone's birthday? Yes?
Just ask them every day.
Yes, January 1st, January 2nd, January 3rd, January 4th, right? Will that work? Yes. Some people say, were you born in January? Were you born in February? You can do something like that and then localize it. There's a lot of good problems you can do. So typically you assume f is continuous. I'm just going to sketch it. Let's say the function is positive at 0 and negative at 1. Because the function is continuous, it has to cross 0 somewhere in between. So then you check it at a half. Let's say it's positive at a half. There must be a 0 between a half and 1. Could there be a 0 between 0 and 1/2? Absolutely. There would have to be at least 2 zeros, either going down and coming back up, or hits the x-axis quadratically. There would have to be an even number of zeros here. So now where do we check? 3/4. And if it's minus, now we know there's a 0 between 1/2 and 3/4. So what do we try next? 5/8. And at this point, we really don't want to do any more. Yeah. The pattern is hopefully clear. How many iterations do I need to say gain 3 digits of decimal accuracy? 10. So any computer science people here? Okay. What ancient Greek or Roman words do you have trouble with?
All of them.
All of them. How many megabytes are there in a gigabyte? 1024. Yes. Now, if you actually use the Greek and Roman correctly, how many should there be? 1,000. But 2 to the 10th is 1024, which is almost 1,000. So the computer scientists have been given special exemption to slightly misuse these words by, less than 3%. Okay? And it's just much more convenient because the computers work in base 2 to say there is 1,000, no, there's 1,024, but we're going to say gigabyte. If you look at the download of a file and it tells you how many megabytes it is, when you get very, very close, it turns to a gigabyte. It goes like 0.9 something, and it changes because it's not 1,000 megabytes as a gigabyte. So every 3 iterations, I'm sorry, every 10 iterations gives you 3 decimal digits. So if you want 6 decimal digits, you have to do it 20 times. If you want 9 decimal digits, you have to do it 30 times. In some sense, this is good, but it's going to be slow. And you are not going to be gaining things quickly. The other thing that is very good about this is the assumptions are very weak. All we're assuming is that our function is continuous. So the idea now is, let's look at a little bit more. Let's say f prime is continuous. So now we want to use the tools of calculus. And the idea is the following. Let's say we have f of x is x squared minus 3, and we want to try to find a root of this. So all of calculus, at least, differentiation comes down to we replace a complicated function locally with a straight line, because locally functions look like straight lines. So we calculate the tangent line. Can somebody give me a reasonable approximation for the square root of 3?
1.7.
No.
2.
Thank you. 1.7 is a good approximation. 2. If I start doing 1.7, it looks like, I'm stacking the deck and I've got somebody planted in the audience trying to help out the professor. I'm wearing long sleeves today. This is very suspicious. But, 2, we all agree 2 is not a great approximation for the square root of 3. If we can do a good job with that as our initial guess. So we have 2 here, and then we have f of 2, which equals 1. We calculate f prime of x, which is 2x. So the slope here, f prime of 2, is 4. So we draw the tangent line. So the tangent line is y minus f of 2 equals f prime of 2 x minus 2. So substituting things in, we get y minus 1 equals 4 x minus 2. And so y equals 4x minus 8 plus 1 is minus 7. So now this is the tangent line. What we do is we say, screw the original function, let's replace it by the tangent line and see where the tangent line hits the x-axis. And that is going to be our next guess. So this was our first point x0, this will be x1. How do you find where the tangent line hits? You take y equals 0, and that gives 4x 1 minus 7 equals 0, so x1 is 7/4, or 1.75. Is that a decent approximation to the square root of 3? Yeah. And now what we do is we do the lather, rinse, repeat method of mathematics. Right? We just keep doing this again and again and again. And you can actually get a nice closed form formula. So if you do some algebra, you get xn plus 1 is 1/2 xn plus 3 over xn. And there are formulas if you want to do cube roots or fourth roots or fifth roots. It just changes trivially. What's a good value of xn to check this on? What would be a good value of xn to check on where I know what xn plus 1 should be if I choose this for my xn?
Root 3.
Yeah, if I take root 3, my next term better well be root 3. And so if I take xn, I get root 3 plus 3 over root 3. That's going to be 2 root 3s divided by root. Good. So xn equals root 3 implies xn plus 1 equals root 3. So once you hit the root, you always stay at the root. In general, you're never going to exactly hit the root. But you can get close. And so it's a nice algebra exercise to show that this is what you get. And then the question is, how good of a job do you do? So x1 is 7/4, x2 is 97/56, x3 is 18,817 divided by 10,864. x4 is a nightmare beginning 708 ... divided by something beginning, I think, 408. What do you notice about all of these numbers?
They're rational.
They're rational. And in fact, as we keep going through this, if you start rational, the derivative will be rational, the point will be rational. When you take y equals 0, the next solution will be rational. So you will always have rational outputs. This is wonderful when you're working on a computer. You will be getting rational approximations. All right. Who knows the digits of square root of 3?
1.732.
1.732. I just happen to be looking down at this piece of paper. I, of course, remember all these. 050,807. I'm just pausing for dramatic effect. Now, I'm trying to remember. My handwriting is a little messy. I think that's a 6,887. x1 is 1.75. Now, remember, how many digits do we gain every 10 iterations of divide and conquer? 3. x2 is 1.73214. It's not bad. x3 is 1.732050810. That was not a swear whoever said damn. That was a remark of
Joy.
I think awe. I like awe. And homage to the great Newton. Okay. We have a fraction, 18,817 over 10,864. We've got 1, 2, 3, 4, 5, 6, 7. We've got over 7 versus 1, 0. The amount we're off by is tremendously small. And that's at x3. I'm not going to even bother writing down x4 or x5, but I will say x5, the error is approximately 8.61 times 10. Now the number is a little bit smaller than what our football team scored, but not by much, to the negative 37. All right. 5 iterations, you're off by basically 1 out of 10 to the 36. And it's a rational number. At this point, goodbye physics. You know, the fact that we can do something this well, and you can prove how well it works. If you've seen fractals, there's a lot of stuff related to fractals that comes from this. And I'll send some stuff later today, really driving this home. Essentially, what happens is every iteration, each iteration doubles the decimal digits. So dinky divide and conquer. 10 iterations get you 3 digits. Newton's method, each iteration doubles your decimal accuracy. If 10 to the negative 36 is not enough for you, if you want 10 to the 100, 2 more and you're there. Why would anybody ever use divide and conquer? Yes? Not all functions are differentiable. Divide and conquer is also much easier to use. We just have to check the sign. So there are advantages. How many of you have taken like a stats or probability course and seen Chebyshev's theorem? Chebyshev's theorem works for any distribution with finite mean and finite variance. The central limit theorem does a lot better in terms of your estimates of probabilities. But Chebyshev can always be used. And so think of that when you're looking at problems like this as to what is the advantage, what is the disadvantage. So really for a lot of the class, this is what I want you to get out of it. The need to be able to get a sense of how efficient is the algorithm. For some things, if you don't need that many digits, divide and conquer is pretty easy to use. Your function doesn't have to be differentiable. But if you really need accuracy, and then what is truly wonderful is there are places where Newton's method does not converge. Or it converges not necessarily to the closest root. And so if there's interest later in the semester, we can talk more about that as to these are stability issues. So I want to just end very briefly with the green problem. All right. So you can go to the OEIS and you can find that we don't know that many terms in the sequence. We've got some values, it becomes conjectural. If you've written the code, you're going, oh great, 1 by 1, 2 by 2, 3 by 3, 4 by 4, 5, whoa. And just the runtime is just growing terribly fast. We will see later how to solve this theoretically using integer linear programming. That doesn't mean we can solve it in a reasonable amount of time, unfortunately. One of the things we can do, however, we can take a step back and ask, what do we really care about? As the board goes to infinity, do you really care how many squares are safe? Instead of how many squares, what would you care about instead that's related to that? What fraction? What if you can show that the fraction of safe squares goes to 100%? Do you really care? If it's n squared minus 5 or n squared minus 25? Or n squared minus something in n? So can we get lower and upper bounds? So I'm going to go fairly quickly. I'm going to do a lower bound. And we're going to overcount. And then I'm going to do the professor's privilege and not worry about integers and floors and whatnot, and just do a quick cut. Let's say we put root n by root n queens down here. How many queens have we placed? That's our n queens. So all we have to do to get a lower bound of the best is find one configuration and see how much is safe there. So here you have the column of death where everything is killed here. You have the rows of death where everything is killed here. And then you have the diagonals of death where everything is killed in here. If we add up those three regions, will that tell us how many things are killed? Will we overestimate a little bit? Yeah, who cares? All right. For the columns of death, how many are killed from the columns? All right, what was it?
Minus n, because you have an overlap on the.
What is this minus crap? No, there is no minus. No. N to the 3 halves. You have to learn to be crude. Okay? Never thought I would say that to a college student. All right, for the rows, how much do we have for the rows? N root n. And that's n to the 3 halves. The point is n to the 3 halves is a power less than n squared. So it doesn't move. Now what about the columns? How many do we have for the columns? Okay, if we do n squared, that's too much.
To be crude.
Well, we can't be too crude. So how many diagonals do we have? Root 2n. So we have at most, say, root 2, root n, I think. Diagonals, right? Yes?
I feel like there's a much easier way to.
Yeah, there are many ways to do this. I'm deliberately being crude because it doesn't matter. I want to show that it doesn't matter. So do we agree that there's at most root 2 root n columns? Modular just bumping any square root of n up to one more than that and using the ceiling. How many entries do you have in each of these? Max n. And so this is at most, n to the 3 halves root 2. So the total is at most root 2 plus 1 n to the 3 halves. I'm sorry? What?
So columns n equals to n 3 over 2.
Oh, yes, this should be plus 2. Yes. And this is why you often just bump things up and put like a 10 there, just to be safe. Well, 2019. The number of spaces is n squared. So the ratio is less than or equal to, basically, root 2 plus 2 divided by square root of n, and that goes to 0. So in the limit, almost every square is safe. There are many other ways you can do the calculation. And a lot of times what would happen is once you prove a result like this, people would say, okay, let's do something a little bit more refined. We know that most squares are safe.
Just for the sake of the recording, do you mean columns, rows, diagonal?
Yes. Thank you.
Wouldn't it have to be 2 root n diagonals? Because then you have a different diagonal for each point along the half the perimeter of that square.
Well, what I'm saying is if you just take the main diagonal here, each one of these is going to create a diagonal.
Yeah, but I'm saying if you walk down the left side and the bottom, you have order of 2 root n squares, and each of those
Coming
are
down here?
diagonals. Yeah.
But each one of these is going to have to hit a diagonal over here.
Yeah, but
Okay.
So then you have 2 root n diagonals, and those are all different. It doesn't matter what they hit inside the square. I'm just saying I think we undercounted our number of diagonals.
I was thinking as long as we get the number of, but I mean we could overcount. We can say there's 1 from here, 1 from here, 2 from here. We could put a 3 over here. We would definitely be safe. I think this is fine. And I think we just need to look at the diagonal here, and then anything over here is going to pass through the diagonal. I might be wrong, and that's why in something like this, it's actually much better, since the answer doesn't matter, to just put in a larger number and just put in a 3 root 2 to be safe. The advantage of doing something like that is if you then make a small error, the whole paper doesn't have to be immediately tossed, and you have to go through it again. If you overestimate, then if you've made a small mistake, you know you're okay from that point onwards. And given that we're saving a square root of n, overestimate. Absolutely. So I think it's fine to do it by just the square root of 2, but I am not confident enough, and the cost is so small, go for it. All right. We have 1 minute left, so for the 1 remaining minute, let's say we do Newton's method to x squared minus 3 equals 0. So there's 2 roots. We'll call this one the, let's see, B and I. Chose 2 letters alphabetically. All right? If I apply Newton's method, if I choose a number that's positive, what root do you think it will go to? Yeah, these should all go to the positive root. If I choose a value that's negative, what should it go to?
Negative.
And if I choose 0, what should it do?
No intercept.
Right. So we will call that P. Right? Red, blue, and purple. Right? I could do x squared plus maybe x cubed plus 1 equals 0. So there are now 3 complex roots. There's a root at -1, then you have 2 other roots in the complex plane. And the natural thing is to say, well, look, split the complex plane up into 3 equal parts, and you should converge to whichever root is closest. And that's true as long as you're not too close to any of the boundaries. And if you are close to the boundaries, this is where fractal behavior happens. And you could be closer to this root, but depending on exactly where you are, you'll go to either one of those 2 roots. It's completely deterministic. But this is where fractal patterns come from. And this is the stability issue of something like this. And this is a big theme that we're not exploring, but in future classes you would look at, is how stable is the algorithm. All right, this is a good place to stop.